Simple harmonic motion. If we hang a mass from a vertical spring, the spring will stretch until it reaches an equilibrium position, where it's undergoing no acceleration. If we pull downward on the mass, we exert a force on it. The mass, in turn, exerts a force on the spring, stretching it. If we let go of the mass, the restoring force from the spring will pull the mass back up toward the equilibrium position. However, according to Newton's first law, the inertia of the mass causes it to go past the equilibrium position, compressing the spring. Ideally, in the absence of friction or air resistance, the spring would compress the same distance past the equilibrium position that it stretched in the other direction. Now that the spring is compressed, the restoring force from the spring once again moves the mass toward the equilibrium position, and the inertia of the mass moves it past the equilibrium position, stretching the spring to the same length once again. In the absence of friction and air resistance, this motion will continue. This motion, that obeys Hooke's law of the restoring force of an ideal spring, is called simple harmonic motion. A system such as an ideal spring that's undergoing simple harmonic motion is called a harmonic oscillator. If we were to attach a pen to the object on the end of a spring undergoing simple harmonic motion and move a piece of paper past it at a constant rate, we could record the position of the object over time. The result would be this shape. This shape is called a sine wave or a sinusoid. This graph shows the position of the object as a function of time. This is the location of the equilibrium position, where the spring is unstrained. These are the locations of maximum displacement, where the object is farthest from the equilibrium position. The magnitude of the difference between the maximum displacement and the equilibrium position is called the amplitude, capital A. When we drew our graph, we chose up to be in the positive direction and down to be the negative direction. So we give the positive maximum displacement a value of positive A and the negative maximum displacement a value of negative A. Previously, we've talked about translational motion in 1 or 2 dimensions and rotational motion. We described these types of motion using displacement, velocity, and acceleration. Simple harmonic motion can also be described in these terms. We looked at displacement on the position time graph for simple harmonic motion, but we'll now find expressions for velocity and acceleration. To do this, we'll relate simple harmonic motion to uniform circular motion. Remember, uniform circular motion implies constant speed. We take a disk that's centered on an axis of rotation and secure a ball to it. We call this our reference circle. We start the disk spinning so that the ball is now moving around the rotation axis of the disk at a constant speed. Next, we put a light to one side of the disk so that the ball casts a shadow on a moving piece of paper on the opposite side. The shadow cast by the ball on the moving piece of paper over time will look like a graph of simple harmonic motion. We'll find an expression for the displacement of an object that's undergoing simple harmonic motion by relating the ball's position on the reference circle to the location of its shadow on the position time graph. Here is our reference circle, and here is our light source. The piece of paper with the position time graph is perpendicular to the reference circle so that we have an edge-on view of the piece of paper. Our reference circle has a radius of A. This vertical line marks a displacement of 0 meters, the equilibrium position. As you can see, it hits the middle of the paper. This line shows the range of possible displacements from the vertical line. If we start the ball moving counterclockwise from this position, we're starting it at the maximum displacement from the vertical line. The ball's shadow hits the paper here which marks the maximum displacement on the position time graph, here. Moving counterclockwise around the reference circle, the ball moves through an angular displacement theta in a time t. Now the ball's shadow hits the paper here, which marks a displacement of about here on the position time graph. Since the ball's circular motion is uniform, it's moving with a constant angular velocity. Remember that angular velocity omega equals the angular displacement over time. We're looking for an expression for the displacement x of the shadow for the new position of the ball. On the reference circle, x is here, and on the position time graph, x is here. Since the radius of the reference circle has a value of a, and since this angle is also equal to theta, we can see trigonometrically that x equals a times the cosine of theta. We then solve the angular speed equation for theta and see that theta equals omega times t. Plugging our theta expression in, we get our final expression for displacement in simple harmonic motion. If the ball moves counterclockwise around the reference circle from the point of maximum positive displacement to a point of zero displacement, to the point of maximum negative displacement, to a point of zero displacement, back to the point of maximum positive displacement, it's gone all the way around the circle one time. We call this a cycle. The amount of time it takes the ball to complete a cycle we call the period, capital T. On the position time graph, the period is measured from here to here, from one point to the next point at the same displacement. If this is a position time graph for our ideal spring, that means the period is the time it takes for the spring to go from its maximum height down and back up to its maximum height. Note that the period could also be measured from here to here, since these 2 points are also at the same displacement. The value of the period depends on the angular speed of the ball. Remember again that angular speed omega equals the change in angular displacement over the change in time. If the ball goes around the circle once during the period, that means its angular speed is 2 pi radians over the period. We can rearrange this to get an expression for the period. The frequency in simple harmonic motion tells us how many cycles are completed each second. 1 cycle per second is called a hertz. If an object in simple harmonic motion goes through 10 cycles per second, then it has a frequency of 10 hertz. If an object goes through 10 cycles per second, that means the period for 1 cycle is 1/10 of a second. Thus we see that the period is inversely proportional to the frequency. Since the angular speed is equal to 2 pi over the period, we can also find the relationship between the angular speed and the frequency. Since omega is directly proportional to the frequency in this way, it's also called the angular frequency. We can use the reference circle to find an expression for velocity in simple harmonic motion. If the ball is moving counterclockwise around the circle in this position, its tangential velocity is given by this vector. We're looking for an expression for this velocity of the ball's shadow as the ball moves from its point of maximum positive displacement toward the equilibrium point. We can see that the velocity of the ball's shadow is just the x component of the tangential velocity of the ball. Using trig, we can see that v sub x equals minus v sub t times sine of theta. The minus sign in this expression is necessary because the velocity vector v sub x is pointing to the left in the direction of the negative x-axis. We know already that theta equals omega times t, and that tangential speed is equal to r times omega. Our value of r for our circle is capital A, so v sub t equals a times omega. We can now plug these in to find our final expression for velocity in simple harmonic motion. The velocity in simple harmonic motion is not constant. At a point of maximum displacement, here and here for example, the velocity is momentarily zero. This makes sense because at maximum displacement, the angle theta is either 0 or pi radians, and the sine of these angles is 0. At zero displacement, here and here, the velocity is at a maximum. The angle theta on the reference circle at the equilibrium position is either 1/2 or 3/2 pi radians, and the sines of these angles are 1 and -1. Plugging in -1 for our sine term then gives us our magnitude of maximum velocity, a times omega. It's important to remember that these expressions are only valid if omega is in radians per second. Since velocity is not constant in simple harmonic motion, there is an acceleration. We can find an expression for the acceleration by looking at vectors on the reference circle. Since the ball on the reference circle is undergoing uniform circular motion, it has a centripetal acceleration, shown by this vector. We're looking for the acceleration of the shadow of the ball, which is the x component of the centripetal acceleration vector. We can see using trig that a sub x equals minus a sub c times cosine of theta. We again have a minus sign, indicating that the acceleration of the shadow is pointing to the left. Again, we know that theta equals omega times t, and we learned previously that the centripetal acceleration equals r times omega squared. Using r equals a again, we see that the centripetal acceleration equals a times omega squared. Plugging these in, we find a final expression for our acceleration in simple harmonic motion. The acceleration also is not constant as time passes. The maximum magnitude of the acceleration is a times omega squared. Remember again that the angular frequency omega needs to be in radians per second. Lastly, with a mass on an ideal spring, we want to find an expression for the angular frequency omega. This is the frequency at which the mass vibrates on the spring. We can do this if we assume that the only force acting on the mass in the horizontal or x direction is the restoring force from the spring. Applying Newton's second law, we find that the restoring force equals the mass of the object multiplied by the acceleration of the object in the x direction. Here we can plug in our expressions for displacement and acceleration of an oscillating spring. Doing so, we get this expression, which we can then solve for the angular frequency. Angular frequency is again in radians per second. You can see from the expression that larger spring constants and smaller masses result in larger angular frequencies. Now that we have expressions for displacement, velocity, acceleration, and angular frequency for simple harmonic motion, we can solve problems involving the motion of ideal springs and other harmonic oscillators.